Hi, welcome to lecture 25. So we want to complete the proof of the main theorem that we left off in the previous lecture. And the main thing that we want to then complete is unique factorization of ideals in Dedekind domains. Okay, just as a summary, so we have a domain and K is a fraction field. And we say that an A module M inside K is a fractional ideal if there exists an alpha that's not zero in A, the property that alpha times M is an ideal of A. Okay, and we defined a Dedekind domain. So we say that A is a Dedekind domain which satisfies three conditions. One is that A is integrally closed. The second condition is that A is Noetherian. And the third condition is that every non-zero prime ideal is maximal. And we wanted to use these definitions to prove the main theorem, which was theorem 56, that every non-zero fractional ideal is invertible. That is, we wanted to show that M times M inverse equals M inverse times M, that equals A, where the set M inverse was this A module with the property that with all the elements alpha and K says that, I'll just write this as alpha times M sits inside A. Okay, and so far what we've shown is that we've shown in lemma 58 that every non-zero maximal ideal, and since we're working with Dedekind domains, every non-zero prime ideal is also maximal, so I could have also said every non-zero prime ideal is invertible. Okay, so that's what we've shown so far. And so now I want to show that every non-zero ideal is invertible. And the proof is very similar. Suppose the assertion is false for the sake of contradiction. Then the following set is non-empty. So if the assertion is false, there must be some ideals, non-zero ideals, that are not invertible. So you take the collection of them, so you take all the ideals, says that I is not invertible. Now again, since A is the Dedekind domain, A is Noetherian. And since by assumption, since the set sigma is non-empty, it must have a maximal element under inclusion. Let's call it I. Okay. By the previous lemma, so we've already shown that non-zero prime ideals or non-zero maximal ideals are invertible. This element I cannot be a non-zero prime ideal. So I cannot be a non-zero prime, and since we are working with Dedekind domains, it's equivalently maximal ideal. But it's still a proper ideal, so it still is contained in some maximal ideal. And again, I can use the word maximal and prime interchangeably since I'm working with Dedekind domains. And again, by the previous lemma, I is not equal to P. Okay, so what we have so far, so I sits inside P. P is an ideal of A, so that sits inside A. And we've shown that A, P inverse contains A. And so again, multiplying by I, we have I sits inside IP inverse. Okay, so it's not hard to see that since I sits inside P, if you take this inverse set, P inverse, this sits inside I inverse. Because I inverse is the set of all elements alpha in K, such that for all x in I, we have alpha times x is in A. Okay. So in fact, since P inverse sits inside I inverse, we can extend this, we can extend P inverse to sit inside I inverse, and so multiplying by I on all sides, we get that I times P inverse in fact sits inside I times I inverse, which sits inside A. Okay. What do we want to show? We want to show, so what we want to show that I times I inverse equals A, but a priori I just know that I times I inverse is an ideal of A. Okay. So thus, what do we have? We have that I times P inverse sits inside A, and hence I times P inverse is an ideal of A. Okay. So again, what do we have? We have that I sits inside IP inverse, sits inside A. Now the claim is that I times P inverse is not equal to I. Okay. Why? Suppose that I times P inverse was equal to I, then again by the proof of the claim, so we've already shown, so we have already shown that P inverse contains A and it strictly contains A, and in the proof we exhibited an element y over x which was in P inverse, but y over x was not in A. Now suppose I had that I times P inverse was equal to I, then using the fact that y over x belongs to P inverse, we have that y over x times I sits inside I. Okay, and now again, since A is a Dedekind domain, it's Noetherian. And so this ideal I is a finitely generated A module. And since we have that y over x takes I to I itself, by the first proposition characterizing integral elements, this is third characterization, we have y over x is integral over A. Again, since A is a Dedekind domain, A is integrally closed. And so this must mean that y over x belongs to A itself, and this contradicts your hypothesis that y over x does not belong to A. So this contradicts the fact that y over x does not belong to A. So the only possibility is that, well, IP inverse contains I, but IP inverse cannot equal I, so it must strictly contain I. So thus, IP inverse cannot be equal to I, and so the only possibility is that IP inverse strictly contains I. And now, using the fact that I is maximal in sigma, and since IP inverse is strictly contains I, we must have that IP inverse does not belong to sigma. But what's sigma? Sigma was the set of all ideals that were not invertible. So if you don't belong to sigma, you must be invertible. So IP inverse in fact is invertible. Thus there exists a fractional ideal J such that the product I times P inverse times J equals A, and then just by associativity we have I times P inverse J equals A. So the product P inverse J is the inverse to I. Okay, and so this shows that I does not belong to sigma, and hence the only possibility is that the set sigma is non-empty, and this completes the proof of the lemma. Okay, so now just combining everything, we can complete the proof of theorem 56 that every non-zero fractional ideal is invertible. So let M be a non-zero fractional ideal, and choose an alpha in A that's not zero, such that alpha times m is an ideal of A. And since m is non-zero and alpha is non-zero, this product alpha m is a non-zero ideal of A. So by the previous lemma, alpha times m is invertible. So let's call this I, and so thus I times I inverse equals A. And so again this means that alpha m times I inverse equals A. And so if we just again by associativity and commutativity, if we just move the alpha around, we get that m times alpha inverse equals A. And so thus alpha I inverse is the inverse, or yeah, is the inverse in some sense to the fractional ideal M. Okay. So thus every non-zero fractional ideal M is invertible, and this completes the proof of the theorem. And so the next main theorem that we want to show for Dedekind domains is that every non-zero ideal I can be uniquely factored as a product of prime ideals. And when I say uniquely factored, the uniqueness is up to reordering. Okay, so you can always write I as a product, say P1, P2, all the way up to PR. Again, I'll leave the uniqueness part as an exercise to the student. This is very similar to how we prove uniqueness once you know factorization in a UFD. So suppose the assertion is false for the sake of contradiction. Then the following set is non-empty. Let's call it sigma, which is the set of all ideals. Say non-zero ideals, says that I does not have a factorization. As a product of prime ideals. And again, since A is the Dedekind domain, A is Noetherian. And now since the set sigma is non-empty by hypothesis, it has a maximal element. under inclusion. So call that element I. And again, I cannot be a maximal ideal, since if it was a maximal ideal, so why? If I is a maximal ideal, is a prime ideal, and you have this trivial factorization I equals I. Okay, but I does not belong to sigma, or I belong to sigma, which means it does not have a factorization. So the only possibility is that I cannot be a maximal ideal. So it in fact is contained in some maximal ideal. And again, since we are working with Dedekind domains, I'll use prime and maximal ideals, non-zero prime ideals and non-zero maximal ideals interchangeably. And again, we know that the inverse of P is contained in A and strictly contains, so P inverse contains A and it strictly contains A. And so multiplying both sides by I, we get that I times P inverse contains I. And again, we've showed, remember that I times P inverse is not equal to I, and so thus I times P inverse strictly contains I, and so by the maximality of I in sigma, we have that I times P inverse does not belong to sigma. And what's sigma? Sigma was the set of all ideals that did not have a factorization as a product of prime ideals. So if you don't belong to sigma, you do have a factorization as a product of prime ideals. And since I times P inverse does not belong to sigma, this means that I times P inverse can be factored or has a factorization into a product of prime ideals, say non-zero prime ideals. So you write I times P inverse as this product P1 up to PR, and so multiplying both sides by P and forming the product ideal. What do we get? We get I times P inverse times P, which is I times P inverse times P. This equals P1 up to PR times P. And so we get I times A equals this product P1 up to PR times P. And so we get that I in fact is a product of prime ideals. And so this gives a factorization of I into a product of non-zero prime ideals, and this contradicts the fact that I belongs to sigma. And so the only possibility is that the set sigma had to be empty, and so this completes the proof of the theorem. Okay, so we've shown that every non-zero ideal of A can be factored as a product of prime ideals, and if you want to do that for a fractional ideal, again it's very similar. So if you have a non-zero fractional ideal, then there exists an alpha that's not zero in A with the property that alpha times m, and let's call it I, is an ideal of A. And so then by the previous theorem, look at the ideal generated by alpha, that can be written as a product of prime ideals. You look at the ideal I, that can be written as a product of prime ideals, say P1 up to Ps. So these are factorization into a product of non-zero prime ideals of A. And so alpha times m, which is I, so if you just combine these factorizations, so alpha times m is nothing but the ideal generated by alpha times m. So what we have is that q1 up to qr times m equals p1 up to ps. So again, multiplying by q inverse or q1 inverse, what do we get? We get q1 inverse times q1 times q2 up to qr times m equals q1 inverse p1 up to ps. So we've removed this prime q1 from the left hand side. We have q2 up to qr times m equals q1 inverse p1 up to ps. And so proceeding iteratively, what do we get? We get that m is q1 inverse, q2 inverse, dot dot qr inverse times p1 up to ps. And so this gives a factorization for non-zero fractional ideals into a product of prime ideals, a product of non-zero prime ideals. But in some sense, we allow negative exponents. Okay. So let's try to summarize what we've studied so far. So in summary, suppose A is a Dedekind domain with fraction field K. Then what we've essentially shown is that the set of non-zero fractional ideals they form a group under multiplication. If you want to multiply two non-zero fractional ideals, you take the finite sum xi yi, where xi belongs to m1 and yi belongs to m2. Okay. So call the set IA, and again the unit element of IA, so call the set IA. The unit element equals a fractional ideal A, and the inverse of a non-zero fractional ideal M equals the set that we define M inverse, which was the set of all elements alpha in K, such that for all x in M, we have alpha times x belongs to A. Okay, and what we also showed is that every element say M of IA has a factorization into a product of prime ideals So if I collect all the prime ideals together, I can write this as P1A1, P2A2, dot PS AS, with the PI's being distinct non-zero prime ideals and these AI's you allow them to be integers, not just natural numbers. And what I left as an exercise was this uniqueness, and we also have this factorization is unique. So this was left as an exercise, and this uniqueness is up to reordering. Okay, and in the previous factorization, I can eliminate all the primes where the exponents are 0, so I might as well assume that these AI's are not 0. Okay. So in other words, what we've shown is that this group IA is in fact a free abelian group on the set of non-zero prime ideals of A. And all this is happening because we've assumed that A is a Dedekind domain. So I want to define a subgroup of IA. So we say that a non-zero fractional ideal is principal if, as an A module, it is generated by one element. So let's call it PA, the set of all non-zero principal fractional ideals and it's not hard to observe that this set PA is in fact a subgroup of IA. Again, if you have a fractional ideal, say M1, and let's say it's generated by beta 1, let's say you have M2, that's generated by beta 2, and it's not hard to see that the product is in fact generated by the product of beta 1 and beta 2. So that's also principal. And if if you want to look at M1 inverse, that's generated by beta 1 inverse. And the identity element again is just A. That's also principal because it's just generated by this one element 1. So you have this group IA and you have a subgroup of it. So you can take the quotient group because everything is abelian. So the class group of A equals this quotient IA over PA, and it's denoted CLA. Okay, so this is what number theorists are interested in studying the class group for rings of integers. And so one of the motivating questions so under what hypothesis on the Dedekind domain A is the class group finite? Okay, so this is sort of motivating question for number theorists, and we like to study this concept of class group when A is a ring of integers. Thank you.